So now let's look at a confidence interval for a variance, and we'll kind of adapt that to be an interval for a standard deviation. So a note to remember is that S squared is a good estimator of sigma squared. The sample variance is a good estimator of the population variance. It's unbiased, it converges, it has minimal variance, and so on. Well, not and so on. Those are the three criteria. We did kind of discuss that when we square root things, we introduce, because of this nonlinear property, we introduce some unfortunate behavior that, for instance, S, the sample standard deviation, is actually not an unbiased estimator of sigma, but it's actually extremely difficult to get an unbiased estimator of sigma. I mean, there's like kind of a whole Wikipedia page on it that talks about all of the difficulties. If you're interested, you can Google it and find that. But for our purposes, we're going to say, okay, we're just going to kind of take as a rule of thumb that S is a good enough estimator of sigma that if we kind of avoid that issue, all of those technicalities, we probably won't regret any decisions that we make, too badly or too often. So we're going to kind of pretend that S is also a good estimator of sigma. We're going to kind of pretend that when we develop a confidence interval for sigma squared, that we can just go ahead and square root everything and then get a confidence interval for sigma. Again, not strictly mathematically precisely appropriate, but we're saying we'll treat it as a rule of thumb that doing this isn't a big deal. We looked before at the distribution of X bar, which I'm trying to select here. I'm not having much luck. We looked at the distribution of X bar. And we said that, well, X bar is it's a statistic, it's a sampling statistic. It's a statistic related to a sample. It has a sampling distribution. There's a distribution of X bar because it's a random variable. Different random samples will give different values for X bar. And it turned out that if we take X bar minus mu over sigma over root n, that was distributed as approximately a standard normal under those assumptions, n bigger than or equal to 30 or normal population. So we took our original statistic we were looking at, we made a transformation by subtracting the mean, dividing by sigma over root n, and then we got in a sense, kind of a standard distribution out of that. Well, S squared kind of has a distribution also, but to get kind of a standard distribution, to get something that's easy to write down on a table or to look up or to understand a little better, we would like to transform S squared in a similar way that we transformed X bar over here. S squared, of course, as we mentioned before, it is a statistic. It's something that for a given data set, you can compute S squared, but that data set came as a result of a random sample. Different random samples would give different data sets, give different S squared. So S squared is a random variable. It has a distribution. And this distribution is such that when I take S squared, I multiply that number by n minus 1 by sample size minus 1. And then I divide by sigma squared, population standard deviation. That yields a chi-squared distribution. This is a distribution that's like Z or like T. It's a certain distribution. So I gave you the chi-square table. We'll talk a little more about what the chi-square distribution is. And then we'll work on this confidence interval. So what is the chi-square distribution? The first thing to note, and I think this is an important note, I'll probably say it a few times, is that the name of the distribution is chi-squared. So this symbol, chi with a superscript 2, is like the symbol Z or like the symbol T. So when we say that's the chi-squared distribution, we don't mean look up a number off of the table and then square it or something like that. The name of the distribution is chi-squared. This thing, this kind of squiggly looking X here, it looks similar to an X, but it kind of has a curly Q on the top, and it's right its bottom right tail actually kind of goes below the line, kind of like, if you had P or Q or something like that, versus say like T or A, the P and Q, the tails go below the line. So the Greek letter chi, its right tail would also go below the line. And I'm not having good success kind of lining things up the right way, but it would look, something along those lines. I might have exaggerated a little bit there, but it would go below that kind of line, similar to how kind of a P and a Q do. So it can look a lot like an X. But I'll try to be careful to say the name of the variable, because I know on your screen it probably looks pretty small, and it probably looks very similar to, like, say an X like up here with X bar. So it might be a little hard to kind of see the difference between a chi and an X. From context you can tell, or I'll try to say the name whenever we're working through it. And of course, if you ever are wondering, you can always ask. But this is the Greek letter chi. That's the Greek letter CH. So in modern Greek, it's kind of like a guttural, like CH, kind of like lock or bach or something like that. And in ancient Greek, it's just kind of the aspirated K sound, like the K sound, like kind of our American K sound. So what is this chi-square distribution? Well, if we consider standard normals, normal mean 0, standard deviation 1, and we construct a random variable as follows. We take n samples from or a sample of size n draws from a standard normal. So I have some standard normally distributed population. I take a sample of size n from there. I take each of those sample values and I square it. So maybe one of the sample draws from the standard normal was, say, 1/2. That might be one of the data points that I got from that population, and I would square it and get 1/2 squared is 1/4. Or maybe another draw was, 2, was z equals 2. I would square that and get 4. I take my sample of size n, drawn from a standard normal. I square each one of those data values, and then I add them all together. This thing is what we call a chi-square distribution. So a chi-squared, the reason that it gets this superscript 2 in its name, it's a reference to the fact that it's made by squaring standard normals and then adding them together. We also note that kind of the more standard normals that we gather, square, and add up, the larger y is going to tend to be, right? So if I add up only, a sample of size 2, if I take my sample, square those numbers, add them together, that's not going to be a very big number. If I have a sample of size 1,000,000, I take all of those numbers, square them, add them up, it's going to be quite a large number. I see the more of these that I add together, the larger the y is going to tend to be. So chi-squared, like t, has a parameter, which we just call degrees of freedom. And in different contexts, the degrees of freedom is different. It is calculated differently, but for this purpose, degrees of freedom, just like t, is going to be n-1. There are some other applications we might get to that use the chi-square distribution at the very end of the course, kind of optional material, and they have some different degrees of freedom calculations. But for this purpose, for the confidence interval for variance and standard deviation, the degrees of freedom is just like the t distribution, n-1. Something else that we might notice is, how did we construct the chi-squared distribution? We took draws from a standard normal. These could be negative numbers or positive numbers. They could be far away from 0 or close to 0. But then we squared them and added them together. By squaring them, we keep the positives positive, but we make the negatives positive. In other words, in essence, everything we're adding together is bigger than 0. I suppose there's like a 1 over infinity chance that it's equal to 0, but in essence, everything is strictly bigger than 0. We're adding together a bunch of positive numbers. Our chi-square distribution is always positive. So our chi-square distribution for a typical degrees of freedom will look something like this. It doesn't go negative. We can't have any negative outcomes. It's only on the positive side. And it also has a large right tail, right? There's some chance that from a standard normal that we draw, as one of our members of our sample, like 10 or something like that, right? Square then I get 100, and that particular draw gives me some hugely large outcome that is, very unusual. But that shouldn't happen very often at all, right? So we have a very unlikely chance of an extreme event to the right. This is right skewed. And this actually kind of makes sense, right? We're using this to, in a sense, estimate s squared, or to say something about s squared. Well, pretty clearly s squared, the variance or the standard deviation for that matter, cannot be negative. So if we had a sampling distribution that went to the negative side, that would seem to be at odds with what we would expect. And we also saw that outliers disproportionately affect the standard deviation, that the presence of an outlier can drastically increase the standard deviation or the variance. And that's kind of reflected in this right skewedness of this chi-square distribution. So maybe this is, for instance, maybe chi-squared with 5 degrees of freedom, where maybe our sample size is 6. If we had chi-squared with, say, 10 degrees of freedom, we would shift over because we're adding together more positive numbers. We would shift over a bit. We would also spread out a little bit. And actually, kind of for fairly large degrees of freedom, the chi-squared almost kind of starts to resemble a normal. It has a long right tail, but if this hump is kind of far to the right, then 0 is kind of far to the left. And that left tail, I mean, it gets cut off at 0, it doesn't go forever, but it doesn't look all that different from a tail that might go to negative infinity, but get very small very quickly. So this is how chi-squared works. The larger the sample size, the more shifted to the right that hump is. So the larger the degrees of freedom, the more shifted to the right that is. Now, let me get rid of this red one. I'm just going to use this picture again. There we go. Let me also get rid of this 5 there. So we'll just work off of this picture so I don't have to draw it again. So now I have a little bit of an issue. I want to develop a confidence interval. I want to find a lower and an upper bound that in some sense kind of respects the symmetry of s squared being an unbiased estimator of sigma squared. Up above, that was a fairly easy thing to do because z and t are both symmetric about 0, about their mean. If I flip the distribution over, it looks the same. I have a bit of a problem here because being a right skewed distribution, it's not symmetric. Chi-squared is not symmetric. If its mean is, let's say, somewhere around here, if I pick it up and flip it over, it looks very different. The tail goes to the left instead of the right. The hump has switched sides. So I have to really ask myself, okay, I still want a lower and an upper bound. I still want to respect symmetry. In other words, when I make an error, when I report an interval that's either too high or too low, and I miss the actual sigma squared with my interval, I want to be as likely to miss below as I am to miss above. I want to be as likely to underestimate as to overestimate on my interval estimate. So the symmetry isn't going to look like s squared plus or minus a margin of error because we don't have the symmetry of the distribution. But the symmetry is going to look more like we want to be equally likely to miss high versus to miss low. In other words, we want it to be equally likely that when we report our interval, when we miss, that our interval will be to the left of the actual sigma squared and to the right of sigma squared. I want those to be equally likely. So what am I going to do? I'm going to report a lower bound and an upper bound that have areas that are equal. And I didn't draw these all that well. Maybe my lower bound should be more like this. In other words, I want this area and this area to both be alpha over 2. So I want to construct a lower and an upper bound where these areas are equal, where this left-hand area that's just a constrained area is alpha over 2, and this right-hand area that's this infinitely long tail is also alpha over 2, half of the error rate. So I want to construct a lower and an upper bound that respect this, but it's really not. So the lower and upper bound aren't going to be actually chi-squared numbers. They're going to be related to chi-squared numbers. So I actually call this chi-squared left because it's the bound that's on the left side. And I'll call this chi-squared right because it's the bound that's on the right side. So when I look up chi-squared numbers off the table, I'm going to look up two different numbers. These won't be negatives of one another because the distribution is not symmetric about 0. There'll be two different numbers. Chi-squared left might be like 5, and chi-squared right might be like 30. I look up these two numbers, and that's what I'll use in my calculation. These numbers with area alpha over 2 to the left of chi-squared left and to the right of chi-squared right. So I maintain this sense of symmetry by having the same area to the left of chi-squared left and to the right of chi-squared right. I lose the symmetry in the sense that these two numbers are not going to be negatives of one another. It might be something like 7 and like 40. Okay, so let's try to construct the confidence interval now that we understand a little bit about chi-squared and what our goals are. So we know that this thing, n minus 1 s squared over sigma squared, is distributed as a chi-squared. So I want to stick n minus 1 s squared over sigma squared in between chi-squared left and chi-squared right, so that this area in the middle here is my confidence level. But I want a confidence interval for sigma squared. In other words, I want to figure out what are the bounds on sigma squared. I don't want the bounds on n minus 1 s squared over sigma squared. I want sigma squared to be the thing that's stuck between two endpoints. If I invert everything, if I take 1 over everything, then inverts this fraction, puts sigma squared up top. That inverts these guys and gives me a 1 over chi-squared left and a 1 over chi-squared right. And by inverting, by doing 1 over, that flips my signs. So the intermediate step is that I have 1 over chi-squared left bigger than sigma squared over n minus 1 s squared bigger than 1 over chi-squared right. And again, this is an inequality that holds with our confidence level. It will hold, say, 95% of the time. And then the last step is I multiply through everywhere by n-1 s squared. These are both positive numbers I'm multiplying by, so none of my inequalities change. Something that's a little strange is that our upper bound uses chi-squared left, and our lower bound uses chi-squared right. That's because these chi-squareds end up on the bottom. So chi-squared right is the larger number. Having it in the denominator, the larger number in the denominator makes the fraction smaller, and chi-squared left is the smaller number of the two. Having the smaller number in the denominator makes the fraction larger. And as I mentioned before, we also need this thing degrees of freedom to know which chi-squared distribution we're using, which member of this family we're using, and degrees of freedom is n-1. So we have a confidence interval for the variance. We have a lower bound, we could call it L, n-1 s squared over chi-squared right, and we have an upper bound, we could call it U, n-1 s squared over chi-squared left. So we notice that it's not something like point estimate plus or minus margin of error. It's like point estimate times n-1 over some chi-squared number. It's going to be point estimate times, on one hand, a number that's bigger than 1, and on the other hand, a number that's less than 1. So we will end up going to either side of our point estimate, but we're not going to have symmetry. We're not going to go the same distance on the independent variable axis to the left as to the right. It's not going to be like s squared minus 0.2 and s squared plus 0.2 for lower and upper bound. It might be like s squared times 0.8 for the lower bound and s squared times 1.3 for the upper bound or something like that. And then so everything we've said so far is what we might call something like mathematically precise. There are a couple of approximations in here to develop this confidence interval, but these are the kind of things where we say for large enough sample size, we can approximately say this. And then we, a little hand wavily, say, okay, well, if I have a confidence interval for the variance, I have a lower and upper bound for the variance, I'll just square root everything to generate a confidence interval for the standard deviation. Is this a mathematically precisely correct thing to do? Well, no, not really. Is it such a bad thing to do that we're going to probably regret doing the confidence interval this way? I mean, probably not. And certainly for the complexity that we would need to add into the system to develop a proper confidence interval for sigma, this seems like a good enough trade-off. If you were going to stake millions of dollars or something on this confidence interval, I would say, well, maybe hire a statistician to do it for you or something. But I think for our purposes, this is good enough. Okay, so let's look at an example. Suppose we're interested in knowing the variance and standard deviation of the masses of dollar coins, those famous ones that look like little gold coins or something. A sample of size 20 yields a sample standard deviation of 0.04111 grams. Assuming normality, compute the 99% confidence interval for sigma squared and for sigma. So one last note about this confidence interval we've developed is this note here, assuming normality. You might think to yourself, oh, okay, we just need to check normality because n is less than 30. But in this case, having an underlying normal distribution is actually quite important. So we really need to check normality for any n. In other words, if we had a sample of size 20 or a sample of size 100, we would need to investigate that sample using some of our techniques from the end of chapter 6 and say, do I think the sample could reasonably have come from a normal distribution? If the answer is yes, then you can proceed with this confidence interval computation. If the answer is no, then you would not want to proceed with this computation for a confidence interval for sigma or sigma squared. Okay, so we know what we need. Well, we have n equals 20. We have s equals 0.04111. Note that we're not given x bar, but x bar observed actually doesn't come up anywhere in this confidence interval. A little bit interesting. The confidence interval for mu includes its point estimate x bar observed, but also the standard deviation. The confidence interval for sigma couldn't care less about the mean. It only cares about the standard deviation. What's our confidence level? 99% tells me that alpha is 1% or 0.01. And n equals 20 tells me my degrees of freedom is 19. So let's bring up the chi-square table that I put in chat. If you bring it up, it looks like this. So we see it actually looks more similar to the t table than to the z table. It's very similar to the t table. This leftmost index column has degrees of freedom. So for instance, this row here with degrees of freedom 10, these are chi-squared indices. These are chi-squared numbers that have to do with the particular chi-squared distribution with 10 degrees of freedom. This row contains numbers that have to do with the particular chi-squared distribution that has 5 degrees of freedom, or 2 degrees of freedom, or 100 degrees of freedom, right? And then we have across the top areas to the right of the chi-squared value. And we see that it's split into kind of two sides. One side where the area to the right is quite a large number, and another side where the area to the right is a small number. These are all areas to the right. Note that for our t table, we only had really one criterion for areas to the right, or one side of the areas to the right, because t is symmetric. So if we could find the area to the right of 1%, then we just take the negative of that t index to get area to the left of 1%. But here we have areas to the right for small areas to the right and large areas to the right. In other words, chi-squared right has a small area to the right, and chi-squared left has a large area to the right. So look up my chi-squared lefts off the left side of the table and my chi-squared rights off the right side of the table. I almost wish they'd have brought this this middle line here all the way down the table just to make it even easier to kind of index off of. Okay, so what do I have? I have degrees of freedom 19. This tells me I want to go to the row corresponding to 19, and I'm going to find my chi-squared left and right numbers off of that. So I'll draw myself a little chi-squared picture here. I want chi-squared left and chi-squared right. I want 99% in the middle, which tells me to the left, I want half of 1%. So 0.01 over 2 is 0.005. Make sure to get enough zeros there. And to the right of chi-squared right is also 0.005. My chi-squared table gives me areas to the right, so I'm looking up for chi-squared right an area to the right of 0.005. But for chi-squared left, I need to look up an area to the right of 1 minus 0.005 or 0.995. So just be a little bit careful about that because the table always gives areas to the right just so that it's consistent and you don't get things backwards or something. It always gives areas to the right. The area to the right of chi-squared left is going to be this 0.995. So if I look at my 19 degrees of freedom row, let's start with the 0.995. I'm looking for the column corresponding to 0.995. I see that's the first column in the 19 degrees of freedom row. That's 6.844. And then chi-squared right, again, 19 degrees of freedom, 0.005 to the right. So I'm looking in my 19 degrees of freedom row. And in my area to the right of 0.005 column, that gives me this number. And I note that if I use the leftmost column for chi-squared left, I'll use the rightmost column for chi-squared right. If I use the second from the left for chi-squared left, I'll use the second from the right for chi-squared right, and so on. So there's a bit of symmetry to the table in that sense that I can also use to just kind of help me index on these things. 38.582. And again, be very careful that chi-squared left is a notation. It's its own thing. So chi-squared left equals 6.844. We don't like take 6.844 and then squared or something. The chi-squared left is already respecting the fact that we've squared a bunch of stuff to get this 6.844 number. Same thing with the 38.582. We don't additionally square that. That is what the symbol chi-squared right represents, 38.582. So I have a lower bound, and we'll start with confidence interval for sigma squared, just to be clear which one we're working on. I have a lower bound and an upper bound. My lower bound is n minus 1 s squared over a chi-squared number. My upper bound looks exactly the same. Chi-squared right is the larger number. If I put the larger number in the denominator, that's the smaller fraction. So chi-squared right is associated with the lower bound because it's in the bottom, and chi-squared left is associated with the upper bound because it's the smaller number going in the denominator. So what is n minus 1? N minus 1 is 19 times s squared, 0.04111 squared. And then chi-squared right, 38.582. And chi-squared left, 6.844. Okay, so I have 19 times 0.04111 squared. I guess I probably didn't need parentheses there, but and then divided by 38.582. That gives me 8 times 10 to the minus 4. So 10 to the minus 1 would be the first decimal place, 10 to the minus 2, 10 to the minus 3, and so on. And my upper bound is the same thing. But here I have 6.844. And I'll just stick a 0 there to get rid of that last digit. So 0.0047 grams for the upper bound. We be careful, 0.0047 square grams for the upper bound because this is for the variance. We notice that these numbers are pretty strange. They're a lot smaller than what we had up here. And again, that's because we're dealing with the variance. So this is our, a common theme of statistics is we have nice math that deals with the variance, but kind of annoying practical results. We have nice practical results that come out of the standard deviation, but sometimes the math is annoying, like having to really kind of fudge things to get a confidence interval for sigma. And my confidence interval for sigma using our kind of rule of thumb that we can just square root everything and we're going to say that we're happy enough for that. Now here, I wouldn't directly square root these numbers. I would say square root my answer, just to be a little more precise, because I run it quite a bit. So when I square root this 0.004 number, I get 0.068 grams for the upper bound. I'm going to second enter twice, or maybe 3 times, to get back to my computation for the lower bound, the one with 38 and so on at the end. Hit enter there. This puts this number that's much more precise than my, heavily rounded number over here into the calculator. And then I'm going to square root that answer. And this gives me 0.028. Let's call it 0.029 grams. So this is probably the more useful confidence interval, saying that roughly speaking, saying that we think that the interval 0.029 to 0.068 is 99% likely to cover the true standard deviation sigma. That's kind of roughly speaking because we were a little bit hand wavy going from one to the other. We could say that more cleanly, that the interval from 0.00083 to 0.0047 is 99% likely to cover the true sigma squared, but that's got funny units and all of that. So often we're going to be more interested in reporting a confidence interval for sigma. Are there questions on any of this? Okay. So a second example. Oh, we did this one already. We can get rid of that. So a second example here. The company produces a certain type of cookie. Our machine is calibrated to produce packages with a mean weight of 32 ounces and a variance of 0.015 square ounces. So we have the variance here. Compute a 95% confidence interval for sigma squared, the variance, on the basis of this sample, where n is 25 and s squared is 0.029. And we say if either bound of this confidence interval is outside of this range, then the company shuts down the machine for recalibration. So basically what we have going on here is we have a sample variance that seems like it's somewhere around twice what we would expect from our machine. Is our machine out of control in a sense, in the statistical sense, in the sense that we want to have quality control? We want to have control over the quality of the product that we're making and manufacturing and sending out. If our machine is operating in a way that is not what we expect and not how it was designed, we want to catch that early on. We want to catch that when there's a small indication, not when like the machine blows up and tears itself apart, or when it sends out a whole bunch of product that really is just not up to our standards. So that's why we might be monitoring these statistics. We want to catch those problems early when they're easier to fix, less costly to fix, less detrimental to maybe the reputation of the company. and we don't want to like have to do some massive cleanup later on, or have a machine that, ends up needing much more expensive repairs because we neglected to fix it when the fix was easier. Okay, so we have a sample. Sample of size 25 with a sample variance of 0.029. And we want a 95% confidence interval. So I have a chi-squared distribution. I have chi-squared right and chi-squared left. I know that I have 95% in the middle, and that the area in these two sides, the one tail and the one just constrained end, the area in these two sides is split evenly. That's the sense of symmetry that I want to maintain, is equal area in either side. So that tells me 2.5% to the left, 2.5% to the right. I know that my chi-squared table gives me areas to the right. So the area to the right of chi-squared right is 2.5%. That's one of the numbers we're going to look up. The area to the right of chi-squared left is 97.5%. That's the other area that we're going to look up. That tells us the two columns we're going to use. We also need to know which row we're going to use. Degrees of freedom is n-1. We're going to use the row corresponding to 24 degrees of freedom. So I see my 24 degrees of freedom row here. This is where I'm going to look up my chi-squared numbers. I can't quite get these I can maybe barely get them on the same picture or in the same window here. But I see that area 0.975 to the right, which is the column for chi-squared left, is the third column over from the left. It's kind of the middle of the left half. And area 0.025 to the right, which indicates our chi-squared right number, is our third column from the right. So, and as soon as I go down here with my cursor, this bar pops up. I wish there was a way to make that not happen, but I kind of see in this 24 degrees of freedom row, 0.975 column, third from the left, gives me 12.401 for chi-squared left. So if I go up here, I had a sample of size 20 and chi-squared left was 6.8. I also had a different confidence level, but this hump is going to be located in different places for different sample sizes. So I don't really have a good idea of expectations for these chi-square numbers, right? I knew that like Z for 95% confidence interval is about 2-ish, right? And because Z is about 2-ish, I know that T is going to be about 2-ish. But I don't have a good gut feeling for these chi-squareds because this hump shifts to the right as sample size increases. So you might look at this and say, that seems so different from the last one. Well, that's because there's just more going on with this chi-squared. That hump, that center is kind of moving left or right based on the sample size and so on. Chi-squared right, again, that has 2.5% area, 0.025 to the right. So we're going down the 0.025 column and across the 24 degrees of freedom row, and that gives me 39.364. And for my confidence interval for sigma squared, which is what I want, I have a lower and an upper bound. They both look like n-1 s squared over a chi-squared number. And again, chi-squared right is the bigger number. It's on the bottom, so it's going to go with the lower bound. Chi-squared left is the smaller number. It's on the bottom of the fraction, so it's going to go with the upper bound. n-1 is 24 in both cases. S squared, well, we have to be careful with what we're given. We're given s squared directly as 0.029. And then over our chi-squared numbers. Chi-squared right is 39.364. Chi-squared left is 12.401. And just as a quick aside, if you had made a mistake and you put chi-squared left here and chi-squared right there, nothing else about these calculations changes. All that you'll have done is you'll have stated in your scratch work that the lower bound is actually the higher number and the upper bound is the lower number. If you just switch the two, you'll be fine. So as long as you pay attention to which you're claiming is the lower and upper bound and which result is actually the lower or higher number, and if you switch them, if you make a mistake, you're fine. So it's not like, 2 or 3 things change and that, that you'll get them jumbled up where you'll have 2 numbers that don't correspond at all to the actual 2 answers. You'll just have the numbers associated with the wrong lower or upper bound, and you just flip them. And so if you're typing into my stat lab or something and you see, oh wait, I said 8 is less than 12 or something, or 12 is less than 8, I just switch that to be 8 less than 12, and for the lower and upper bounds. So just as an aside, it's not like the end of the world if you get the chi-squared left and right swapped. You just realize that at the end and put them in the right order. Okay, so what do we have? 24 times 0.029 over 39.364. Oh. 39.364. 24.029 looks good. So that's 0.018. And then we'll do second enter, reuse much of this, and we have 12.401. So that's 0.056. So we can say that we are 95% confident that the interval from 0.018 to 0.056 covers the true variance sigma squared. Now I have a range that I'm interested in. This is not a confidence interval, but this is just a range that I'm interested in. If either bound of the confidence interval, the lower or the higher, is outside of the range 0.008 to 0.030, I'm going to shut down the machine and recalibrate it. I note that 0.018 is indeed in the interval 0.08 to 0.030. Right, 0.01 is like between 0.00 and 0.03, but 0.056 is not in the interval 0.08 to 0.030. 0.056 is above 0.030. That upper bound of this 95% confidence interval for sigma squared is too high. We are concerned that on the basis of the sample, we're concerned that our machine is putting out cookies with a higher variance than it was designed to. That might be an indication that something's going wrong with the machine or the process. We want to shut down the machine, shut down that production line, have a technician go over, look at the machine, fix it if needed, or whatever, get things back under control before we start that line back up and making more product.